there is a photograph that exists now that should not exist. It shows galaxies. Hundreds of them. Spirals and ellipticals, red giants and blue dwarfs, scattered across a patch of sky smaller than a grain of sand held at arm's length. But these are not ordinary galaxies. These are ghosts, echoes of light that have traveled for over 13 billion years to reach us. Light that left its source when the universe was barely 300 million years old. When there were no planets, no stars as we know them, nothing but hydrogen, helium, and darkness. And yet there they are, fully formed, mature, impossibly bright. The James Webb Space Telescope took this photograph, and in doing so, it broke cosmology. This is not hyperbole. This is not clickbait sensationalism. This is the quiet panic spreading through astrophysics departments across the world, the growing realization that our most fundamental models of how the universe works may be wrong. Not slightly wrong. Not in need of minor adjustments. Fundamentally, catastrophically wrong. If you want to understand what's happening at the edge of human knowledge, if you want to follow the only channel documenting this unraveling in real time, subscribe now. Because what we're about to explore will change how you see reality itself. The James Webb Space Telescope is not just a larger version of Hubble. It is an entirely different kind of eye. Hubble sees in visible light, the same wavelengths your retina detects. But Webb sees in infrared. It sees heat. It sees the stretched, red-shifted photons from objects so distant that the expansion of space itself has pulled their light beyond the visible spectrum into the deep red and infrared. To do this, Webb's mirror is coated in gold. Not for aesthetics, gold reflects infrared light better than any other practical material. That mirror is 6.5 meters across, made of 18 hexagonal segments that had to unfold in space like a mechanical flower, each positioned with nanometer precision. A single error would have turned a $10 billion instrument into orbital junk. And it must be cold. Colder than you can imagine. Webb orbits at Lagrange point 2, a million miles from Earth, where a 5-layer sunshield the size of a tennis court keeps it at negative 233 degrees Celsius. At this temperature, the telescope's own heat doesn't interfere with the faint infrared whispers from the early universe. This is not just engineering. This is prayer made manifest. Humanity begging the cosmos to reveal its secrets. But here's what we didn't anticipate. Sometimes the cosmos answers. And sometimes the answer is not what you want to hear. Before Webb launched, we had a story about the universe. A good story. A story built on mathematics and observation, refined over decades. It went like this. In the beginning, 380,000 years after the Big Bang, the universe was smooth. Nearly perfectly smooth. Tiny quantum fluctuations in density, frozen into the fabric of space during inflation, were the only irregularities. Over hundreds of millions of years, gravity amplified these fluctuations. Denser regions attracted more matter. Dark matter clumped first, creating gravitational wells. Then ordinary matter, hydrogen and helium gas, fell into those wells, heated up and ignited. The first stars were born. These stars were massive, short-lived, and exploded quickly as supernovae, seeding space with heavier elements. Gradually, over 1 billion years, these stars clustered into the first galaxies. Small, irregular, chaotic, like children learning to walk. Only after several billion years would these proto-galaxies merge and evolve into the grand spirals and ellipticals we see in the local universe today. That was the model. Lambda CDM. Lambda for dark energy, CDM for cold dark matter. The standard model of cosmology. The framework that explained everything from the cosmic microwave background to the large-scale structure of galaxy clusters. Webb was supposed to confirm this story. to photograph those early, primitive galaxies in their infancy, to watch them fumble and grow. Instead, Webb photographed monsters. They appeared in the very first deep field images. Objects with designations like GLASS Z13 and CERS 93316. Galaxies with redshifts indicating they existed just 300 to 400 million years after the Big Bang. But they weren't small. They weren't primitive. They were massive. Billions of solar masses worth of stars. Mature stellar populations with complex structures, disks, bulges, spiral arms. The kind of architecture that should take billions of years to form, not hundreds of millions. The initial reaction was denial. These must be measurement errors. Redshift contamination. Dust obscuration mimicking high redshifts. Photometric redshift is tricky. You're estimating distance based on how light is distributed across filters, not from spectroscopic lines. Surely spectroscopic follow-up would reveal these objects were closer, less extreme. But spectroscopy confirmed it. These galaxies are exactly as distant and as impossible as they appear. The numbers are obscene. To form a galaxy with 10 billion solar masses of stars by redshift 13, you need star formation rates that exceed anything we observe in the local universe. You need essentially all the available gas in a region to turn into stars with near-perfect efficiency. No feedback. No supernovae blowing gas away. No quenching mechanisms. Just relentless, impossible creation. And there's not enough time. Even if you started forming stars the instant the first atoms formed, even if you worked at maximum theoretically possible efficiency, the universe is simply too young. It's like finding a fully grown oak tree in a garden that was planted yesterday. Let me explain why this is impossible. Star formation is not instantaneous. It follows a process. A molecular cloud collapses under its own gravity. As it collapses, it fragments into smaller clumps. Those clumps heat up. Eventually, the core reaches 10 million Kelvin and hydrogen fusion ignites. A star is born. This process takes time. Millions of years for the collapse. Then the star must live its life, fuse hydrogen, evolve, possibly explode. If it explodes as a supernova, it enriches the surrounding gas with heavy elements, which slightly changes the properties of the next generation of stars. You can model this. You can calculate how quickly a galaxy can build up its stellar mass given the density of gas, the efficiency of star formation, the feedback from supernovae and stellar winds. The limit is called the Eddington limit for accretion, and star formation efficiency maxes out at around 10% under ideal conditions. But the galaxy's Webb seas require efficiencies near 100%. They require essentially every atom of gas to become a star. They require the laws of thermodynamics to politely step aside. And there's another problem: cooling time. Before gas can collapse to form stars, it must cool. Hot gas has pressure. Pressure resists collapse. Cooling reduces pressure. But cooling takes time for atoms to radiate away their energy as photons. In the early universe, there are no heavy elements to facilitate cooling. No carbon, no oxygen, no metals to radiate efficiently in the infrared. Just hydrogen and helium, which cool slowly. The time required to cool, collapse, form stars, and build a massive galaxy is measured in billions of years. Not hundreds of millions. So how did these galaxies do it? We don't know. It gets worse. Webb has observed the rotation curves of some of these early galaxies. Rotation curves tell you how fast stars and gas are moving at different distances from the galactic center. In the local universe, rotation curves are flat. Velocity stays roughly constant even at large distances. This is the primary evidence for dark matter. There must be a massive, invisible halo of dark matter extending far beyond the visible galaxy, keeping those outer stars moving faster than they should. But some of Webb's high-redshift galaxies don't show this. Their rotation curves drop off. They behave as if there's no dark matter halo, or far less than there should be. This resurrects an old ghost, modified Newtonian dynamics, or MOND. The idea that maybe we don't need dark matter at all. Maybe gravity just works differently at low accelerations. MOND has been dismissed for decades because it doesn't fit the cosmic microwave background or galaxy cluster data. But what if MOND is right in the early universe and wrong later? What if gravity evolves? What if dark matter doesn't exist at high redshift because it hasn't formed yet, or behaves differently? These are not fringe ideas anymore. Papers are being published. Serious cosmologists are reconsidering frameworks they dismissed as crackpot theories. Because if dark matter doesn't explain what we're seeing, then one of the pillars of modern cosmology is made of sand. While galaxies break our models on the largest scales, exoplanets break them on the smallest. Webb has observed the atmospheres of dozens of exoplanets by watching starlight filter through their atmospheres during transit. The spectrum tells you what molecules are present. And what Webb found is disturbing. WASP 96b, a hot Jupiter, shows clear signs of water vapor and clouds. Expected. Beautiful, but expected. K2-18b, a sub-Neptune in the habitable zone of a red dwarf, shows methane, carbon dioxide, and, most controversially, possible traces of dimethyl sulfide. DMS. On Earth, DMS is only produced biologically, primarily by phytoplankton. Let me be clear, this is not confirmed. The signal is tentative. It could be noise. It could be a misidentification of another molecule. The error bars are large. But the mere possibility, that Webb has detected a biosignature at 120 light-years away is psychologically overwhelming. Because if it's real, then life is not rare. Life is not special. Life is a cosmic commonplace, scribbled into the atmospheres of worlds we cannot reach, cannot touch, cannot ever visit with our biology. And Webb can't tell us for sure. It sees the shadow of molecules. It sees spectral lines. But it can't zoom in. It can't send a probe. It can only whisper, something is there. Maybe. This is a new kind of hell. Knowing without knowing. Seeing without seeing. Population 3 stars. The first stars. Born from primordial gas with no metals, no carbon, no oxygen. Just hydrogen and helium. Theory says they should be massive, hundreds of solar masses. Short-lived. Exploding as pair-instability supernovae that leave no remnant, seeding space with the first heavy elements. Webb was supposed to find them. These stars should exist at the very edge of the observable universe, their light stretched to the deepest infrared. But we haven't found them. We found their consequences, the heavy elements in later galaxies, the enriched gas. But the stars themselves? Absent. Maybe they're too faint. Maybe they lived and died so quickly that the odds of catching one in the act are astronomically low. Maybe our models of their properties are wrong. Or maybe they never existed. There's a heretical idea circulating. What if the first stars weren't massive? What if they were small, long-lived, and still burning today, too faint for Webb to see individually, but contributing to a diffuse background glow? If population 3 stars are different than we think, then our entire understanding of nucleosynthesis, the process that built the periodic table, needs revision. The absence of evidence is becoming evidence of absence. And that absence is terrifying. Gravitational lensing is one of the universe's gifts to astronomers. When light from a distant galaxy passes near a massive foreground object, a galaxy cluster, the gravity of that cluster bends space-time, magnifying and distorting the background galaxy. Sometimes you get Einstein rings, perfect circles of light. Sometimes arcs. Sometimes multiple images of the same galaxy scattered across the sky. Webb has observed hundreds of lensed galaxies, and among them, anomalies, transient events, flashes that appear in one epoch of observation and vanish in the next. Not supernova-like, not gamma-ray bursts, something else. Some researchers think they're seeing magnified, lensed supernovae, individual stellar explosions magnified by gravitational lensing to the point where they become visible across cosmic distances. But the timescales don't always fit. Some flashes are too fast, some too slow, some recur. There's speculation, wild speculation, that we're seeing caustic crossings. Regions where the lensing magnification becomes infinite for a brief moment due to the alignment of multiple lens structures. A star in the background galaxy passes through this caustic, and for hours or days, it's magnified a millionfold. Or maybe it's something we haven't thought of. An astrophysical phenomenon with no name. A signature of physics we don't yet understand. The lensed ghosts flicker in the data, and we write papers, and we speculate, and we don't know. Redshift is how we measure distance in cosmology. As the universe expands, light is stretched. The amount of stretching tells you how far away an object is. There are two ways to measure redshift: photometric and spectroscopic. Photometric redshift is fast. You look at how bright an object is in different filters, ultraviolet, optical, infrared, and fit a model to estimate the redshift. Spectroscopic redshift is slow but precise. You spread the light into a spectrum and identify specific emission or absorption lines: hydrogen, oxygen, carbon. The wavelength shift of those lines gives you the exact redshift. Normally, these methods agree, but Webb has found galaxies where they don't. Objects where the photometric redshift says Z equals 10, but spectroscopy says Z equals 8. Or vice versa. At first, this seems like a technical issue. Photometric redshift can be fooled by dust, unusual stellar populations, or strong emission lines. But the pattern is too common, too systematic. Some researchers are quietly asking, what if the expansion of the universe isn't uniform? What if there are local variations in the Hubble parameter, regions of space expanding faster or slower than average? This would violate the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. An assumption that underpins all of modern cosmology. If the cosmological principle is wrong, then the entire framework of lambda CDM collapses. We can't trust our distance measurements. We can't calculate the age of the universe. We can't even be sure that the Big Bang model is correct. The redshift anomalies are small. They might be noise. They might be instrumental systematics. But if they're real, we have to start over. Between redshift 1 and 3, roughly 7 to 11 billion years ago, the universe experienced its peak of star formation. Cosmologists call this cosmic noon. The sun was brightest at midday. After cosmic noon, star formation was supposed to decline. Galaxies ran out of gas. Supermassive black holes turned on, blowing gas away. The universe should have gotten quieter, dimmer, more settled. But Webb's data shows cosmic noon extending further back in time than expected. Galaxies at redshift 5, 6, 7, when the universe was less than a billion years old, are forming stars at rates comparable to cosmic noon. The universe didn't gradually build up to a peak. It was already at the peak. This means the early universe was far more active, far more violent, far more energetic than we predicted. Gas was somehow more available. Cooling was somehow more efficient. Feedback mechanisms were somehow less effective. Or, and this is the disturbing thought, our models of star formation are wrong. Not slightly wrong. Completely wrong. If we can't predict star formation, the most fundamental process in galaxy evolution, then what can we predict? Here's something most people don't realize. The data we've seen so far from Webb is a tiny fraction of what exists. There are thousands of observations sitting in archives, waiting to be analyzed. Entire sky surveys that will run for years. Programs targeting specific objects in wavelengths and sensitivities never before achieved. Right now, somewhere in a FITS file on a server, there's a spectrum that will rewrite a textbook. A galaxy that will break a theory. A pattern that will reveal a new law of physics. And no one has looked at it yet. Because data analysis takes time. It takes expertise. It takes PhD students spending months writing code to extract signal from noise, to calibrate instruments, to cross-reference catalogs. The discoveries we're discussing, the impossible galaxies, the strange atmospheres, the redshift anomalies, these came from the first datasets released. The low-hanging fruit. The deep truths are still buried, hidden in noise, waiting in statistical correlations that require analyzing thousands of objects to detect. There are researchers who spend entire careers on a single survey. They'll publish their first results in 2 years, their final results in 10. And only then will we know what Webb truly found. The silence in the data is the loudest sound in astronomy right now. Webb cannot do this alone. We're building a network of instruments to cross-reference, confirm, and extend Webb's findings. The extremely large telescope in Chile, a 39-meter optical telescope that will achieve resolutions matching Webb but in visible light. Launch targeted for 2028. Nancy Grace Roman Space Telescope, a wide-field infrared telescope that will survey vast regions of sky, finding rare objects that Webb can then study in detail. Launch 2027. ALMA, the Atacama Large Millimeter Array, already operational, observing cold gas and dust in the early universe, complementing Webb's stellar observations. And beyond, missions in planning stages to detect gravitational waves from supermassive black hole mergers, to measure the 21-centimeter hydrogen line from the cosmic dark ages, to build telescopes on the far side of the Moon, shielded from Earth's radio interference. Each instrument sees the universe differently. Each wavelength tells a different story. Only by combining them, optical, infrared, radio, X-ray, gravitational waves, can we assemble the full picture. But here's the terrifying possibility. What if even that's not enough? What if the universe operates on principles that no electromagnetic or gravitational wave detector can reveal? What if the key to understanding the anomalies lies in physics we haven't discovered yet? Dark sector particles, extra dimensions, quantum gravity effects. Then we're not just missing pieces of the puzzle. We're missing the puzzle itself. Let's think about what it means if lambda CDM is wrong. Lambda CDM is not just a model. It's the foundation of cosmology. It tells us the age of the universe, 13.8 billion years. It tells us the composition, 5% ordinary matter, 27% dark matter, 68% dark energy. It tells us the fate, eternal expansion into cold, dark infinity. Every measurement, every observation, every interpretation is filtered through lambda CDM. It's the lens we use to see the cosmos. If that lens is cracked, then nothing is certain anymore. How old is the universe? We calculated that age using lambda CDM. If lambda CDM is wrong, the universe might be significantly older or younger. Does dark matter exist? Maybe. Maybe not. Maybe it's a placeholder for physics we don't understand. Will the universe expand forever? We assumed dark energy is constant. What if it's not? What if it decays, or strengthens, or reverses? These aren't academic questions. They're existential. They determine whether life has a future in this universe, whether intelligence can survive the heat-death, whether consciousness is a brief accident or a cosmic inevitability. And here's the deepest fear. What if the universe is fundamentally incomprehensible? What if reality operates on principles so alien to human intuition that we're biologically incapable of understanding them? What if we're like ants trying to grasp quantum mechanics, equipped with brains that evolved to find food and avoid predators, now aimed at the structure of space-time itself? Maybe the anomalies aren't solvable. Maybe they're the point where human cognition reaches its limit. Or maybe, and this is the hope, we're on the verge of a revolution. A paradigm shift as profound as relativity or quantum mechanics. A new framework that makes the impossible galaxies, the strange redshifts, the missing stars all suddenly make sense. But revolutions are painful. They destroy careers built on old ideas. They render textbooks obsolete. They force us to admit we were wrong. And scientists, like all humans, hate being wrong. There are patterns emerging that we don't talk about yet. Patterns too subtle, too uncertain to publish. Gaps in stellar mass distributions. Certain mass ranges where galaxies seem rarer than they should be. Possibly a selection effect. Possibly real. Asymmetries in the cosmic infrared background, the diffuse glow of all the starlight ever emitted. Regions slightly brighter in some directions than others. Could be foreground contamination. Could be real structure in the early universe. Correlations between galaxy properties and large-scale structure that are statistically weak but persistent. The kind of thing that shows up at 2 sigma significance, not enough to claim a discovery, but too strong to ignore. These are the signals that keep researchers up at night. The ones they mention in conference talks but hedge with caveats. The ones that need more data, more statistics, more time. But they're there, waiting. And the thing about anomalies is they tend to cluster. One anomaly might be a fluke. 2 might be coincidence. But 5, 10, 20 anomalies pointing in the same direction? That's a revolution waiting to happen. There are thousands of observations in the pipeline that haven't even been made public yet. Entire surveys that will run for years. Missions planned to pair Webb's results with new instruments, ones that'll look in other wavelengths or catch up in resolution. And then there are the things we haven't even imagined yet. The surprises. The quiet anomalies. The strange patterns in background galaxies. The leftover questions from redshift measurements that don't quite align. The weird atmospheres. The gaps in stellar mass. The lensed flashes that might be something more. Because the thing about a telescope like this is, you never really know what matters until you look. And when you finally do, it's never what you expect. Webb has looked deeper into space than any instrument in human history. It has seen further back in time, closer to the beginning, than we ever thought possible. And what it found is not comforting. It found a universe that doesn't follow our rules. A cosmos that refuses to be tamed by our equations. Evidence that everything we thought we knew might be a simplification, a child's model of reality, adequate for the small corner of space-time we inhabit, but hopelessly naive when applied to the full scope of existence. This is not the end of cosmology. This is its rebirth. Painful, chaotic, exhilarating. We stand at the edge of the known universe, staring into a darkness that stares back with galaxies that should not exist, with stars that refuse to form, with physics that bends in ways we never predicted. And we have a choice. We can retreat into the comfort of our old models, dismiss the anomalies as errors, wait for more data to smooth out the contradictions. Or we can leap into uncertainty, into the unknown, into the glorious, terrifying possibility that the universe is stranger, deeper, more beautifully incomprehensible than our ancestors ever dreamed. The James Webb Space Telescope is humanity's eye on the cosmic abyss. And the abyss is looking back. What we do with that knowledge, how we respond to the revelation that we are smaller, more ignorant, more wonderfully insignificant than we believed, will define the next chapter of human understanding. The data is there. The anomalies are real. The questions are waiting. And somewhere, in the cold silence a million miles from Earth, Webb continues to observe, continues to collect photons that have traveled for billions of years to reach its golden mirror, continues to whisper secrets that we are only beginning to hear. The universe is not what we thought, and we are not done looking.